Okay, so today is Tuesday, and I got a lot of kids gone, so we're gonna hammer through the assignment, we're gonna introduce the lab, and then we'll go from there. All right, so here's the basic idea of what you should be able to understand at this point. When something's moving around in a circle, whether it's the Earth going around the sun, where it's the sun going around the center of the Milky Way galaxy. In the lab, you're going to have a rubber stopper that you're going to swing around on the end of the string. Mother Nature doesn't like circles, okay? Mother Nature goes, that's a lot of work. I'm not into it. Mother Nature prefers straight lines at constant speeds. So if you see something speeding up, slowing down, or changing direction, that's acceleration. That's going to require a force. So when you look at how you can calculate this, what's on your equation sheet is that you have AC equals V squared over R. Okay, you go through the calculus to see where that comes from, but it's basically the rate of change of your velocity vector. Boom, there you go. So from that, you can go, oh, centripetal force equals mass times centripetal acceleration, which you can also write as mv squared over r, okay? So if you have the velocity, it's a simple calculation. Plug it in, boom, you're off to the races. But there's a couple of things that you need to remember about that centripetal force and the centripetal acceleration. First and foremost, it always acts inward. That's why it's called centripetal, okay? Because it comes from the Greek word meaning inward seeking. There is nothing pushing it out. Does it have inertia? Yes. Does it want to move in a straight line? Yes. Okay? But in the lab, when you take it and you swing this rubber stopper around over the top of your head, you are not emanating a force field that's going to push this rubber stopper out. The sun is not emanating a force field pushing the Earth towards the outside. The Earth has a tremendous amount of mass. The Earth has a tremendous amount of inertia. So it takes a tremendous amount of force to keep us following around the sun. So there's three sources of this force. Friction is one you all use most of the time. Okay? It's the friction between the tires in your car. So if you look at mu equaling force friction over force normal. So if you're on a flat surface, which is what we're going to be on, so if I take this binder clip and put it on the green spinny thing, okay, and I have that going around like this, it's friction that's creating the centripetal force that allows this thing to move around in a circle. So if you look at the forces acting on, so here's your green spinny thing. So here's that binder clip. So you've got gravity pulling it down, you got the normal force pushing it up, and then you have that centripetal force acting towards the inside. So if it's the string's going to create the centripetal force. If it's friction, that's what's going to create it. If it's the Earth going around the sun, gravity is going to create that force, okay? So the unique thing about this is that if you look at this in terms of variables, and you go, oh, well, my force friction is what's creating my centripetal force, and I'm on a flat surface, so that's the same, that's my gravitational force. So then you can get a little bit fancier, and you can go, oh, that's mass times centripetal acceleration. That's m over g. The masses cancel out. It's a ratio of centripetal acceleration to your gravitational acceleration. That's one option. Now, in the lab that you're going to do today, you're going to take a rubber stopper, and you're going to swing that around on the end of the string. And you're going to measure the period, and you're going to measure the radius, and that's going to allow you to calculate the circumference. So the other way that you can do this is that you can use, V equals 2 pi r over t. If you substitute that into the acceleration equation, that becomes 4 pi squared r over t squared. Substitute it in, square it, one of your r's are going to cancel out. This is what you're left with. So, centripetal force equals 3 things. It equals mass times centripetal acceleration. It equals mv squared over r. It equals mass times 4 pi squared r over t squared. Okay, so those are the 3 equivalent statements for centripetal force. But they all act inwards at a right angle to the velocity vector. So if you look at question number 1, okay, you got a runner, got his mass, got the radius, traveling with a velocity of 8.42. What's the centripetal acceleration? On number 1, all you're going to use is just v squared over r. You got the velocity, you got the radius, boom, there you go. Then to get the centripetal force, on B, just take your answer from A, multiply that by the mass. Then it says, oh, what's the coefficient of friction? So that coefficient of friction, you can either take the ratio of your centripetal acceleration to your gravitational acceleration, or if you're old school and you actually want to work with forces, you can take that centripetal force that you just found, take its mass, multiply that by g, there you go. So that coefficient of friction on 1c should be around 0.2, okay? So what that means is that that's the minimum coefficient of friction. So to make this happen, so if the coefficient of friction between the shoes and the track is like 0.8, hey, you're golden. But if that coefficient of friction is only like 0.1 because it's icy, then you're not going to make that turn. Okay. Your answer to number 3 should be around your age right now. Your answer to number 4 should start with a 4. So if you look at questions 3 and 4, 3 and 4 are basically the same question, just a slightly different twist. So on 3 and 4, on both of those, you're starting with the idea that centripetal force equals mv squared over r. And again, something has to create that centripetal force. The tension in the string, friction between the tires and the pebble. Something has to keep that in place because Mother Nature doesn't like circles. So what you have to pay attention to on number 3, number 1 is a 25-gram pebble. Make sure you convert that into kilograms. Also, as Danny pointed out, when you look at that problem on number 3, I've given you the diameter of the wheel, not the radius. So you have to pay attention to the fact that that's the diameter. Now, when you get to question number 5, a youngster on a carousel 5 meters from the center revolves at a constant rate, making 1 complete revolution in 15 seconds. So here's the story. One of the things you've got to be able to begin to figure out is sort through whether I've given you frequency or whether I've given you period. So if you look on that one, you're making 1 complete revolution in 15 seconds. That's period, okay? Because we're saying 1 revolution is 15 seconds. Now, if we said that she made 15 revolutions in a second, which would be really, really fast if you consider someone on a carousel going 15 revolutions per second. So, but if I said that, which I didn't, then that would be frequency because that's revolutions per unit of time. Okay, so that's one of the things you need to sort out. On number 7, and thankfully our rock is accelerating towards the sun. By the way, speaking of things that are in orbit, if you do want to see that comet, it's pretty cool. If you go out, here's kind of a visual marker, and I figured this out last night. So if you go out shortly after sunset, and it's going to be cool because it's going to basically, there's going to be a full moon rising in the east, and there's going to be a comet in the west. So on the west, you're going to see about, this is looking straight west. Kind of off to your left a little bit, you're going to see a very, 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 very bright star. That's actually the planet Venus. Okay, so that's Venus. Then if you go over about 2 fists and then up about 2 fists, that's about where that comet is going to be. Now, I couldn't see it with the naked eye, but if you take your camera on your phone and put it up there, that's when I was able to take a pretty good picture of it. So it's cool tonight. So it's going to be a full moon on one side and a comet on the other side, on opposite sides of it. So anyway, but it needs to be done pretty shortly after dark. All right. So your answer to number 7 should be something times 10 to the minus third. Now let me give you a hint. So some people get tied up and they work number 7. They use 2 pi r over t. They found the velocity of the Earth, and then they put that into v squared over r. You can do that, but it's a god-awful amount of work. Okay, it really is. Just use, if you can just go straight to 4 pi squared r over t squared. Okay, you can just do it in one calculation. You don't have to calculate the velocity separately and then put that into v squared over r. Just do it in one step. Okay, you can do it just now. When you're changing that 1 year into seconds, and this is a number we're going to be using a lot when we get into gravitational calculations. When you change that into seconds, do not round that number, okay? You keep all of those seconds. That is not a measured value, okay? So when you convert that year into seconds, you keep all of those seconds. Do not round it. You keep all of the seconds in a year. Now, on number 10, so let's talk about that one. So, here's the centrifuge. There's your center. That test tube is in here like this, and this forms a 30-degree angle. And the test tube is, 100 millimeters long. Okay, so here's what you got to do. So this one, the center of this thing is 5 centimeters. Okay, so that gets you to the edge of the test tube. Then you got to use sine to figure out how far the bottom of the test tube is from the top of the test tube. Okay, so you're going to have 2 different dimensions. You're going to have this, which is 5 centimeters. This is in millimeters. Convert everything into meters. So your radius is going to be from the center out to that edge. Okay, so you got to take the 5 centimeters, convert that into meters. Take the 100 millimeters times the sine of 30, get the side opposite. Convert that into meters, add the 2 numbers together. So on this one, you're told that it spins at 4,000 revolutions per minute. So there's a couple of things you can do. One option is that you take the 4,000 revolutions and divide that by 60. So Preston, if I take the revolutions and divide it by seconds, is that period or is that frequency?
Frequency?
Yeah, because it's revolutions per second. So one option is that you can because it wants you to calculate the centripetal acceleration. So one option is that you can just use 4 pi squared r times f squared, because 4 pi squared r over t squared, that's period and frequency are inverses of each other. So if you come in here and go, oh, that's 4 pi squared r, and then 1 over frequency squared, the frequency flips up. So the beauty of this is that you don't have to do another conversion. You can just take the 4,000 divided by 60, figure out how many revolutions per second that is, slam that right into that equation. Okay, that's it. That's all you have to do. So the next question asks for how many g's. So this is one of the things you can talk about even on the lab today. So g's is a reflection of how many times greater the acceleration is than normal gravitational acceleration. So right now, if you want to get talk nerdy, you can say, hey, I'm pulling 1 G. So if your college application says, hey, what's your superpower? I pull 1 G. Okay, everyone does. Just not you. So when you go to lift your arm, you're used to lifting your arm under an acceleration of 9.8 meters per second squared. Gravity is pulling it down and you have to overcome that. So if you're under 2 Gs, your body would be accelerating at 19.6 meters per second squared. So what that means is that when you go to lift your arms would feel twice as heavy as they do right now. So if you've ever been in like on an amusement park ride where it spins you really fast, which we'll get into later, if you're feeling like, oh, I feel heavy, it's because you're experiencing an acceleration greater than 9.8 meters per second squared. So now this hint is going to test your knowledge of American history. So the number of G's on number 10 should be a little bit more than the year we signed the Declaration of Independence. Okay? So that is the centripetal acceleration. This is the number of G's. A little bit more than when we signed the Declaration of Independence. You're sitting there going, 1812? No, that was a war. Okay? So now, let me give you some perspective. So that's about, roughly about 1,800 Gs. So typically people pass out at about 2 to 3 Gs, okay? Once you hit about 15 to 20 Gs, that's when bad things happen to your body, okay? So if someone shrinks you down, like in the movie Ant-Man, and they go, oh, hey, we're going to put you in a centrifuge, don't go. Bad things are going to happen. Basically, you're going to turn into a little pink spot on the bottom of a test tube, okay? So if you ever get shrunk down, like in the movie Ant-Man, do not go into the centrifuge. Just saying. On number 11, so let me kind of give you that visual. You're swinging, this is where projectile motion meets a lemming problem. So you're swinging this ball around over the top of your head in a horizontal plane. And it is 1.8 meters above the ground. So if you remember yesterday, swinging the rubber stopper, I let go of it, boom, it turns into a projectile. It's a lemming problem. You can figure out how long it takes for that ball to fall 1.80 meters. Oh, x equals 1/2 at squared plus v naught time. Vertically, your initial velocity is 0. Find your time. So your time, because if that's wrong, everything is going to be wrong. So your time should be around 0.6 seconds. So that's true whether I drop it or this thing goes flying off like a projectile. So on number 11, your time is around 0.6 seconds. Now, you're told that it lands 4.4 meters away. So if this thing goes flying, it lands 4.40 meters away. Cool. So you know how long it's in the air, and you know range equals Vx time. So you know how far it travels, 4.4 meters. You know how long it's in the air, so you can figure out how fast it had to be going to turn into a projectile and travel that far. Then once you get that, then you can plug that into mv squared over r. So if all goes well on number 11, that answer should be pretty close to your current age. Okay? So your answer to number 11 is close to your current age. So let me kind of recap. Your answer to number 7, with the sun, that's 10 to the minus third. Your answer to number 8 is 10 to the third. Your answer to number 9 is 10 to the negative fourth. So here's your sequence. 7, 10 to the minus third. 8, 10 to the positive third. 9, 10 to the negative fourth. Okay? And your answer to number 11 is something close to your current age. Cool with that? All right, any questions out of the problems in the book? Cool with those?
Just 10.
Was that with the wind turbine?
The centrifuge. Yeah, that's what I think so too. It's page 1084. 184 actually.
Oh, that's in.
Yeah, it's the wind turbine one.
Yeah, the wind turbine. Okay, so wind turbines are cool. That's just me though. So here's the story. So you got this wind turbine. Obviously, it's going to undergo centripetal acceleration because of the fact that it's moving in a circle. So on number 10, it says, one company makes a turbine for use on land with blades 40 meters long that spins at 17 revolutions per minute. So this thing is 40, okay? Spins at 17 revolutions per minute, okay? So revolutions per minute, Danny, is that frequency or period?
That's frequency.
That's frequency because it's revolutions per minute. So then what they want to know is at what rate should the blades of the offshore rotate if the speed at the tip is to be the same back as the turbine on land. So here's what you want to look at. So you want the tip of that be spinning at the same rate as that one is, okay? So that's what you want to have happen. But here's the problem. It says they're twice as long. So if this is spinning at 40 revolutions per minute, and no, it's 40 meters long, and it spins at 17 revolutions per minute. So, well, if this thing is going to be twice as long, so if you look at V equals 2 pi r over t, so you want the end point of both of those to be the same. So you want the exact same velocity on both sides. Okay, now you could actually go through and calculate that velocity if you wanted to. You could take the 40 meters, boom, you could use 2 pi rf, take 17 and divide it by 60, boom, there you go. And you would get that velocity. Okay, so that's the velocity of the 40 meter one. So then you can go, okay, well, I want the same velocity, 2 pi, but now my radius is going to be twice as big. So if my radius jumps from 40 up to 80, and if I want the same velocity, what has to happen to the frequency? It has to be
What?
other way.
Greater, bigger? Yeah, greater.
Nope. Look, you want the same velocity here, right? You want the same velocity. So, and that's 2 pi rf. So if I double the radius and I want the same velocity, what has to happen to the frequency? If I double the frequency, I'm gonna quadruple my velocity. Rhymes with half.
Half it.
Yeah, it's going to be half as much because you're doubling the radius, so your frequency has to become half as much to end up with the same velocity. There you go. Okay. Now, let me give you some hints when you answer a question like problem like 13. Okay? You want to rank these in from largest to smallest, the tensions in the string. When you're going to do a lot of problems like this in this class, here's what I don't want. You're going to start off and you're going to say, hey, like let's say for example, on number 13, you think number 3 is the smallest one, which it is, okay? So, because you're going to rank these from largest to smallest, okay? There you go. So what you want to do next is put in like operators. Put greater than, less than, equal to. I don't do commas. So I can do greater than, I can do less than, I can do equal to. So a question like number 13, and you're gonna have a lot of questions like number 13. So let me give you a hint. You're gonna start off and say, okay, number 3 is greater than number 1. So let me give you a hint. That's your beginning sequence. Number 3 is a greater tension than number 1. Now, number 1 might have the same tension as something else, okay? Or it might be something. But do not, on a question like number 13, do not use commas. I don't do commas because I don't know what commas means. You can do greater than, you can do less than, you can do equals. Do not just write down commas. I will flip out because I don't know what commas mean. Okay. Anyway, there we go. Anything else? We're good? Okay. So let me stop that and we'll start the lab.